2.8. Graphing linear inequalities in two variables. A linear inequality is an inequality in two variables whose graph is a part of the coordinate plane separated by a line. A boundary is the line of the inequality. These are two graphs showing linear inequalities. These two lines are boundaries. The boundary separates the coordinate plane into two parts of the plane. One part of the plane consists of solutions of the inequality. The shaded region consists of solutions of the inequality. You shade one part of the two parts of the plane to show the solution set. These two shaded regions are the solution sets of the two linear inequalities. To determine which half plane to shade, pick a point on one side and check if it makes the inequality true. This is called a test point. Now, let's practice. First, I graphed the boundary line for the inequality. I used a dashed line since it simply said greater than, not greater than or equal to. Then I tested a point not on the boundary line, for example, 0, and determined whether it was a solution of the inequality. It was not, so I shaded the other half plane. Number 2. First, I isolated our variable y. Then, I graphed the boundary line for the inequality. I used a solid line since it said greater than or equal to. I tested 0 once again, and it did match, so I shaded that half of the plane.
Because y describes vertical position, the solution of y is greater than mx plus b will be above the boundary line. The solution of y is less than mx plus b will be below the boundary line. You should graph absolute values the same way you graph linear equality. The line will be dotted if the inequality symbol is less than or greater than. If the inequality symbol is greater than or equal to, or less than or equal to, the line should be solid. You can also write inequalities from the graph. First, you would find the slope-intercept for the linear equality. To graph 5x minus 2y is less than or equal to negative 10, try finding the x and y intercepts. To do that, substitute one or the other of the variables with 0. First, we'll find the y-intercept by substituting x with 0. Because 5 times 0 is equal to 0, divide by negative 2 on both sides, giving you y is equal to 5. Do the same thing for x, but this time substitute y with 0. So because 2 times 0 is equal to 0, divide by 5 on both sides, giving you x is equal to negative 2. Now that you have your two intercepts, plot both of them onto the graph. Now because it's a less than or equal to equation, your line will be solid. To find out which side to graph, use a test point. Because 0 is not greater than 5, you would shade the upper side. Use the original function and translations for an absolute value inequality. To graph absolute value of x plus 1 is greater than y plus 7, you want to isolate y by subtracting 7 on both sides, giving you x plus 1 minus 7 is greater than y. Now there are two ways you can graph this. You can graph it y is equal to the absolute value of x, translated 1 unit to the left because it's positive 1 plus 1, and then 7 units down because it's minus 7, or you can create a table and put these numbers for x over here and to get your y. You plot the points. Because it's only greater than and not greater than equal to, your line will be dotted. To find if you shade inside or outside the graph, try inputting the test point. Because 0 is not less than negative 6,
here is some practice for writing inequalities. Write inequalities for each graph. Let's start with graph 1. Graph 1 is a combination of 3 inequalities. Find each one individually. Start with the first blue line. You can tell that the y-intercept is 2. Find the slope just like you would for an equation. The slope is negative 2/3. The equation of the boundary line is negative 2/3 x plus 2. To convert this to an inequality, first you need to determine what sign to use. The boundary line is solid, so you know to either use greater than or equal to or less than or equal to. Since the shading is to the left and below the line, we can assume that the sign is less than or equal to. To check, pick a test point in the suggested solution set. 0, 0 is a great example. Once you have confirmed that the test point works and you know the inequality is y is less than or equal to negative 2/3 x plus 2, then you can find the other two inequalities. They are x is greater than or equal to 0 and y is greater than or equal to 0. Shade in all three solution sets. Wherever all the shaded areas overlap is the final solution set. For graph 2, once again, find the equation of the line. The equation is negative 2/3 x plus 2. Since the shaded region is above the boundary line, the inequality is either y is greater than negative 2/3 x plus 2 or y is greater than or equal to negative 2/3 x plus 2. It is greater than or equal to because the line is solid. For graph 3, the boundary line equation is the same as graph 2. However, the shading is below the boundary line, so the final inequality is y is less than or equal to negative 2/3 x plus 2. For graph 4, the equation of the line is y equals 0. Since the shading is above the boundary line, the inequality is y is greater than or equal to 0. The challenge question for this lesson is, what is the difference between a half plane for a less than or greater than inequality and one for a less than or equal to or greater than or equal to inequality? The answer is simple. For less than or greater than inequalities, the boundary line will be dashed because values on the line are not possible solutions. For less than or equal to or greater than or equal to inequalities, the boundary line is solid, indicating that the values on the line are solutions.